This meeting is now being recorded.
Good afternoon. I'm Beverly Anderson, and I work for the State Water Board and the Surface Water Ambient Monitoring Program, or SWRCB, and I'm the lead on a number of cyanobacteria harmful algal bloom projects being funded by SWRCB. The talk is going to be a little bit different from future talks, as there won't be a lot of emphasis on data visualization. Since this project is so new, we're still working to build the infrastructure needed to collect and analyze data. Cyanobacteria, or blue-green algae, are found in most kinds of water bodies and worldwide. They can exist as single cells or as colonies and can form blooms that cover entire lakes. In September last year, there was a balloon 600 miles long on the Ohio River, and the Klamath has seen the effects of blooms through up to almost 200 miles of river. Some of these blooms are relatively harmless, although they may be unsightly and be associated with taste and odor chemicals. But some species of cyanobacteria release one or more toxins that can cause skin irritation, liver damage, and in the case of one toxin, antitoxin A, can cause very rapid onset of symptoms such as vomiting and convulsions, and even death in dogs and livestock that ingest it. There are also some non-cyanobacteria species that can form harmful algal blooms, like Primesium or golden algae in Southern California, which produces toxins that can cause massive fish kills. This week, a fish kill was reported from a reservoir in Nevada that could affect the recreational fishing there for several years. And we've seen similar fish losses in some lakes in Southern California from Primesium. Because of these increases in frequency and severity of HABs statewide, and the fact that there was no consistent program to address them, it was identified that California was in need of a freshwater HAB strategy. These increases have variously been linked to increasing temperatures, high nutrient flows that support bloom growth, and the current drought with subsequent low flows and warmer, slow-moving water where blooms tend to build up. Since there has been a marine HABs program started as a requirement of the FDA for decades, the SWRCB program was developed to focus on the freshwater systems. Cyanobacteria generally originate and bloom in freshwater bodies, such as lakes and wetlands. However, blooms can also occur in rivers and streams, and we're starting to see more of that with the current drought conditions. In addition, rivers and streams can act as a conduit, delivering cyanobacteria and their toxins to other areas downstream, such as estuaries and marine waters. The most common toxic cyanobacteria in California is Microcystis. It can produce several toxins, with variations of microcystins as its primary toxin suite. Other cyanobacteria can also produce microcystis. In 2012, OEHA set a recreational human health action level for microcystins of 0.8 micrograms per liter. And then just last year, the U.S. EPA set a drinking water human health advisory for microcystins of 0.3 micrograms per liter. We're also starting to detect antitoxin A and cylindrospermopsin, as well as other cyanotoxins throughout the state. We have several hotspots in California where toxic algae blooms have been recurrent, including the Klamath, Clear Lake, Pinto Lake, and the San Francisco Bay and East Bay Delta Lakes. We're starting to see blooms and toxins in lakes and rivers that have not previously experienced them. And Southern California lakes have been experiencing blooms of golden algae, which are causing massive fish kills, as I mentioned earlier. I'm going to quickly go over some of these hotspots in the next few slides. In the Klamath River Basin, they've been detecting toxin concentrations between 1,000 and 10,000 micrograms per liter microcystins. Let me remind you, the OEHA recreational action level is 0.8. liter. This region has developed one of the most advanced cyanobacteria monitoring programs in the western U.S. In Clear Lake, the main impact of cyanobacteria is on drinking water. There are 18 drinking water intakes around the lake, shown by these red diamonds. It serves 44,000 plus people with drinking water. Clear Lake has cyanobacteria blooms through much of the year, and although toxin levels are generally below 20 micrograms per liter microcystis, lower than some of the other hotspots in California, they're still well above the U.S. EPA drinking water threshold of 0.3 micrograms per liter. So intensive monitoring and high levels of treatment are required at these drinking water locations. Additionally, monitoring is being done in recreational use areas, and toxin levels have been detected in the range seen in the Klamath, in the thousands to 10,000 levels. Satellite imagery has been used for several years to detect blooms in Clear Lake. This kind of monitoring can allow for an early warning if a bloom is detected. This photo shows an image from February 2013, where the blue color indicates little or no phycocyanin or chlorophyll A in the main body of the lake. And this one from July 2011, where the oranges and reds indicate high levels of the pigment, triggering potential need to test for toxins. Another one of our hotspots is Pinto Lake. Pinto Lake provides an example of how cyanobacteria blooms in freshwater can have impacts on the marine environment. Several years ago, sick and dead sea otters were found on the beaches of Monterey Bay. Since then, more than 30 dead sea otters have been found. The deaths were determined to be from Microcystis, which was carried downriver from Pinto Lake and taken up by bivalves. These bivalves were then eaten by the otters, leading to liver failure and eventual death. These photos show the jaundice in the mouth and chest cavity from liver failure. This is an example of a land-bay connection between blooms in lakes and effects in bays. Pinto Lake's seasonal cyanobacteria blooms can have toxin concentrations averaging around 1,000 micrograms per liter. In the East Bay Lakes, the summer of 2014 saw 2 toxic cyanobacteria blooms. Lake Temescal was closed to swimming for half the summer. Lake Chabot had a bloom that only diminished for brief periods since it started and resulted in 3 dog deaths. In 2015, there were toxic blooms in 6 of the park's lakes. In the Lake Chabot in the Vallejo area, there was 1 dog death. All of the lakes that allowed swimming were closed to swimming where there were toxic blooms. The bloom in Lake Chabot reached a high of 150,000 micrograms per liter in a sample collected from scum. Then in December, just last month, there was a bloom in Lake Dalval where there are drinking water intakes. In addition, there was a dog death associated with anatoxin A in the Russian River, with the toxin being detected for weeks after the incident. As a response to statewide blooms, the freshwater HABs, SWAMP has developed an assessment and support strategy and funded some of the infrastructure necessary for the successful implementation of the strategy. The goal of the strategy is to have a program to assess, communicate, and manage freshwater HABs in a collaborative fashion. The strategy was developed around a SWAMP freshwater HABs program, which is providing funding for several projects to support satellite monitoring of blooms, as well as the infrastructure needed to support response to bloom events. These projects are based on several goals defined by the California Cyano HAB Network and mainly fall under the infrastructure component of the strategy. The strategy itself has 3 components: response to events, ambient monitoring, and risk assessment, which are divided into a water body scale level, The immediate event response at water body scale level would start in response to positive satellite imagery hit for phycocyanin, like the image we saw of Clear Lake, or some other evidence of a bloom, and would inform public notification and bloom management. The updates to the 2010 draft voluntary guidance document include a flowchart of this process from initial identification of a bloom to posting, with toxin and other triggers for various types of posting. Long-term event response includes the development of local action plans and possibly TMDLs, or total maximum daily loads, and the implementation of management and remediation strategies. The strategy also calls for regular monitoring of water bodies with recurrent blooms or those at high risk of blooms. This monitoring may start with visual inspections and advance when blooms are detected. Local water body managers and other agencies can much more readily mobilize for frequent or event-based monitoring, and the Klamath monitoring program is an excellent example of this. At the state and regional scale, the strategy calls for monitoring on a large spatial and temporal scale that would consist of adding cyanobacteria and toxins to ongoing monitoring programs and would not be event-based. The purpose would be to track spatial and temporal trends, and SWRCB is already starting to follow this recommendation with some of the programs it has for ambient monitoring. Risk assessments to determine water bodies which may be most at risk for blooms can be conducted by several methods. Identification of high-risk water bodies would lead to regular monitoring. There's also a large infrastructure component in the freshwater HAB strategy. I'm going to go into that now briefly. The infrastructure part of the strategy consists of 7 components, many of which are being funded by SWRCB. SWRCB has funded SFEI, San Francisco Actuary Institute, to download and analyze satellite imagery to notify water body managers of blooms, to evaluate temporal trends, and for a biweekly bulletin and quarterly newsletter. A centralized website is also being developed in coordination with the CCHAB for data storage, visualization, and access. This website will be a portal of the California Water Quality Monitoring Council. The strategy includes the development of a number of event response guidance documents. The first is the CCHAB voluntary guidance document, which is being updated currently. The second is a SWRCB-funded document that includes protocols for sampling in multiple types of water bodies and analysis of samples. And the third describes remediation and management measures for freshwater HABs. SWRCB has also provided some funding to assist with initial lab toxin and cell identification tests. SWRCB conducted several training courses in the summer of 2015 that taught basics of identification and dealing with cyanoHABs, and will be expanding on these courses in 2016. SWRCB is also planning a workshop on management and remediation of blooms in 2016. Applied research and outreach are 2 important areas with minimal funding. Applied research is needed to be able to identify by satellite imagery blooms in water bodies smaller than 250 acres. Some work is being started on this. Several new methods of early detection are also being investigated and may provide future cost-effective ways of monitoring water bodies. These include the use of phycocyanin probes, benchtop fluorimeters, flow cams, and various methods of detecting toxin genes. Further development on remediation measures is also needed. The outreach component calls for increasing public awareness to increase recognition, reporting, and public safety. This can be done through fact sheets, webinars, social media, focus groups, etc. Outreach should be geared toward healthcare professionals, veterinarians, policymakers, public agencies, and the public. It'll also include the development of communication and coordination protocols for agencies responsible for water bodies at the freshwater HAB. This can best be developed at a regional level. So thank you. If you have any questions, I think we have a little bit of time for me to respond.